You know, when you open the Uber app, it feels so simple, doesn't it? You see where you are, you see the cars moving around, you get a price. But behind that super simple screen, well, there's an engineering marvel at work. So let's dive into the absolute magic that makes your Uber app feel so instantaneous. All right, I want you to just take a guess. Think about every single person opening the app, every driver on the map, every price getting calculated, all at the same time, all around the world. What do you think that number is? A million? Maybe 10 million? 150 million. Yeah, that's the real number. Every single second, Uber systems are fielding 150 million requests for data. It's just a staggering figure that's kind of hard to even wrap your head around. So what exactly are these 150 million requests? Well, the engineers call them reads, but for you and me, they're basically the invisible heartbeats that make the entire app experience work. Every single one of these things is a read. Every time the app refreshes your location on the map, that's a read. Checks your driver's ETA, another read. Shows you the cars nearby, or if there's surge pricing, yep, you guessed it, more reads. Now multiply that by millions of users all at once, and you get to that insane 150 million per second number. Now, you can probably imagine that trying to handle a constant tsunami of data like that is not easy. And this is where we get to the real core engineering problem that Uber had to solve. Think of a normal database like a single, very, very busy librarian. Now, if 150 million people all scream for a book at the exact same time, that librarian is going to crash hard. The whole system would get incredibly slow, or even worse, just fail completely. And that's not exactly what you want when you're just trying to get a ride home, right? So Uber basically had a choice to make. They could have gone the obvious route and just bought thousands and thousands more databases, just throw money at the problem. But that's not only incredibly expensive, it doesn't really solve the core speed issue. Or they could do something much harder, but way, way smarter. Innovate. Build a truly intelligent system from scratch. And well, they chose the smarter fix. And that smarter, really elegant answer can be summed up in just one word: caching. This is the secret weapon that makes the whole thing possible. This analogy just nails it. Instead of making our busy librarian, the main database, run to the back of the building for the same popular book over and over again, you just put a copy of it on a special, super fast, most popular shelf right at the front desk. And here's the more official definition. That most popular shelf is what engineers call a cache. It's a high-speed storage layer that sits right between you and the main database, holding copies of the most frequently asked for data, so it can be delivered almost instantly. Now, of course, Uber didn't just use some off-the-shelf caching solution. Nope, they built their very own, custom-tailored system designed for their massive scale. It's called CacheFi, and it acts like a brilliant high-tech shield for their main databases. CacheFi uses a strategy called a look-aside cache. The logic is actually pretty simple, but it's incredibly powerful. The app is programmed to always look in the super-fast cache first. If the data it needs is there, bam, that's called a hit and you get your answer instantly. If it's not there, that's a miss. Then and only then does it bother the main database. And here's the key. It then takes that answer and puts it into the cache so the next person who asks gets a hit. But this system creates a new, really fascinating problem. What happens when thousands of people ask for the exact same missing piece of data all at once? The engineers have an awesome name for this: a thundering herd. And if you're not careful, that herd can stampede right past your cache and crush your database anyway. So how does Uber handle this herd? Okay, their solution is just brilliant. CacheFi is smart enough to see this whole herd of requests arriving for the same thing. And it basically picks just one request and says, okay, you're the leader. Only you get to go to the database. Everyone else, all the followers, they just wait. Once the leader gets the data, it puts it in the cache and then shares it with all the followers at the same time. The herd is managed and the database stays safe. CacheFi has another really clever trick up its sleeve too. It's called negative caching. This is so smart. If you ask for a piece of information that doesn't exist, it actually remembers that the answer is nothing. This stops the app from asking the database the same pointless question over and over again, which, believe it or not, saves a ton of wasted effort.
So after all this brilliant engineering, what was the result? I mean, what was the real-world impact? Well, it was absolutely massive.
This chart says it all. This is the payoff. A staggering 95%. 95% of those 150 million requests per second are now handled by the super fast Cachefe system. Only a tiny 5% ever even have to talk to the slower core databases. I mean, that completely changed the game for them. And hey, don't just take my word for it. The Uber engineering team themselves said it best. This huge reduction in load meant the app was way more reliable. And on top of that, it led to a massive drop in hardware and operational costs. It was a total win-win. So the next time you open that Uber app and you see those little cars just gliding smoothly across the map, you'll know. All of this incredible, complex engineering, the thundering herds, the leader-follower models, the negative caching, all of it exists for just one simple reason: to create that seamless, simple, and totally instantaneous experience for you. It's an absolutely amazing achievement. But it does leave us with one last thought. They solved for 150 million requests per second, but as our world gets more and more connected, what happens when we need a system that can handle 1 billion? What new kinds of innovations will that take? Now that's the next great challenge.